Ever seen a boat slide faster than the tide with zero wake? That's the claim around Atlas, an object that sped up near the Sun with no visible exhaust. If the rocket effect needs billions of tons of gas, where's the plume? Stick with me. In December, JWST and Hubble look straight at Atlas. If they don't see that massive cloud, we're left with two choices: rewrite how momentum works for comets, or admit we're staring at unknown propulsion. I'll show you the test, the numbers, and why this ghost current matters to every model we trust. Before we move on, I'd like to ask you a small favor. If you appreciate this content, please take a second to like this video and subscribe to the channel. Over 98% of you watch the videos without subscribing. It costs you nothing, but it makes a huge difference to us. So, did you click the subscribe button? Great! Thank you so much. Now, back to the video. Out on the water, a fast hull with no wake sets off alarms. Same deal here. Atlas picked up speed near the Sun while looking clean, no exhaust, no flare, no broad fan of dust.
These jets are naturally produced out of ice on the surface of a rock. And the second possibility is that they might be thrusters on the technological spacecraft. Well, thanks for having me. We see more than 7 jets that are tightly collimated coming out of this object. And of course, there are 2 possibilities that we considered all along.
Is it streaming out? What is all this? Is it breaking up after possibly going behind our Sun? A little confusing because this all comes after last week images showed the object with no tail. Weird.
So let's dive in. Acceleration needs a push. For a comet, the push is gas boiling off and shooting out. That's the rocket effect. Hot jets kick one way. The body drifts the other way. Here's the rub. Reports say the speed change is real, but the usual signs don't match. No bright plume. No fat, soft tail. No clear glow that screams mass loss. Think of a boat throttling up. The wake widens. The bubbles tell you where the power goes. If the surface stays glassy while the speed climbs, you're not watching a motor. You're in a strange current. Standard playbook says water heats, vents, drags dust, and builds a tail. We track the non-gravitational drift to those jets. When the water share runs low, strong thrust gets harder to source. You can swap in CO or CO2, but each leaves a trace. If 5.5 billion tons left in a month, that's a sky-wide fog bank. Thin per cubic yard, yet spread over a huge volume and bright at the right bands. So watch how we check.
And so how do we tell the difference? Well, if it's a natural object, then we know the temperature on the surface of a rock, given its distance from the Sun. And even after it passed through perihelion, it was heated by 770 watts per square meter. And we know that the previous plume of gas was mostly carbon dioxide. And carbon dioxide ices can sublimate at a much lower temperature than water ice. So we should have seen it break up, or at the very least disintegrate to a very dense and massive cloud of gas and dust that is pushed away from the Sun.
Big glass can sniff this out. Infrared tags warm dust and CO2. UV and optical pick up water lines and the way light scatters off grain sizes. Polarization tells you if the particles are fluffy or glassy. Thermal maps show where the heat moves. Ground arrays fill gaps and confirm time trends. December turns into our field test. A cloud that big would hang for days and show up in more than one channel. If it's there, the data stack lines up and the thrust ledger balances. If it's not, the push came from somewhere else, and that's a harder knot to cut. Next up, we set the rules for that check: what lines to watch, how bright the cloud should scan, and what a clean frame would say about the source of the shove. If a 5.5 billion ton wake exists, how bright is it, and what's the fastest way to spot it? Out on the water, you don't scan every ripple, you check the signs that pop. Same here. We run a tight checklist: gas lines for water, CO2, and CO, dust brightness, tail shape, how the light polarizes, and any nickel or iron hints if metal grains show up. Now, there's talk of a dry mix and odd polarization. That leans away from a giant steam plume. It doesn't rule out a strong CO or CO2 driver, though. So we don't guess. We test the wake the way you read a quiet bay with sonar when the surface looks calm. Infrared and spectroscopy are the sonar. They read through the chop.
We've got some updates. Check out these new images that show 3i Atlas in a whole new light. What's going on with this situation? What are these jets?
Before they have a chance to turn around and show up as a plume of glow behind it, away from the sun. That's one possible interpretation, but otherwise I just don't know what to make of it. So what I'm saying is, you know, there are things we don't fully understand about this object. That's what makes it exciting, and I think all of us will wait for the data that will come in the coming weeks.
Let's dive in. JWST's infrared looks for heat and the fingerprints of CO2 and CO. It also tracks warm dust and sizes the grains by how they shine at different colors. Hubble, on the UV and optical side, tags water bands and shows how dust sizes spread by color and by polarization. When those two views line up, you get grain size, gas mix, and tail structure in one clear picture. The trick is cross-check. If a plume that large is real, more than one instrument will call it. Think of two depth finders pinging the same reef from different angles. You want the same bump at the same spot, across days, not a one-frame spike that fades. Set the bar in plain terms. Big mass loss means a steady, multi-day signal in gas lines, a tail that holds shape as it turns, and dust that stays bright in the bands that match the gas driver. That's the wake. You'll hear chatter about directional coincidence and the track hugging the ecliptic. Log it as context. Keep the test simple: wake or no wake. If the wake shows, momentum math stays clean, and Atlas sits in the wild but natural box. If the sky stays clean, we ask the push question for real. Now you know what to watch. Let's say what that does to the maps we use, from com. Physics keeps score. If there's thrust, there's a wake. If there's no wake, something new is pushing. As the source says, physics is crystal clear. Massive acceleration requires massive mass loss. So watch December's data drops. Check the lines for water, CO2, and CO, check dust brightness, tail shape, and polarization. Match the checklist across days. If this helped, subscribe and come back for clear reads as results land. If the sky stays clean and the speed holds, the map changes. Comet playbooks shift. Propulsion ideas get a hard look. Next up, we track how those changes ripple through every chart you trust.